All right, let's talk about some stoichiometry with thermochemical equations. This is a lot of fun, not least because you get to say that wonderful word stoichiometry. Okay, let's look at an equation. What makes this a thermochemical equation? Well, we're going to take this equation where we have aluminum oxide, otherwise known as bauxite, a mineral. And we're going to decompose it into, I almost put an arrow instead of a plus sign, that was weird. Okay, into aluminum and oxygen. It's a great way to make aluminum for aluminum foil and aluminum, all the other things we use aluminum for. What makes this a thermochemical equation is the fact that stuck out here to the right a ways, we have this delta H, and we put Rxn down there to show that this delta H is for a reaction, not just a temperature change that's happening with, warming something up or cooling it down or whatever. But it's really not a big deal whether you write Rxn there or not, as far as I'm concerned. As long as you get your delta H, that's the key thing. Now, sometimes in order to indicate that it costs us some energy, we have to put heat into this thing to make it happen. Sometimes all we do is we put a little triangle over the arrow. That's not the same thing as the delta in front of the delta H. This is just actually a real triangle, not a delta. And that triangle symbolizes that you have to put heat in to make it happen. But a lot more specific way of writing this is to say exactly how much heat we have to put in, and that's to show the delta H. Well, in this case, it takes 1676 kilojoules of energy to make this reaction happen. Well, how much? How much is reacting? Well, 1 mole of aluminum oxide is reacting to form 2 moles of aluminum, and isn't this odd? 3/2 of a mole of oxygen. So we have 1 mole of aluminum oxide making 2 moles of aluminum and 3/2 mole of oxygen. The reason this 3/2 is here is because a lot of times we're taking the key chemical that we care about the most in this equation, and we want to know the amount for 1 mole of it. We could rewrite this equation and just double everything, and it would look a lot more normal to you. And I'm going to just double the coefficients plus 3 O2s. And of course, this is still a solid, this is still a solid, this is still a gas. But since I have 2 moles now, I would have to double the delta H. And the delta H, oh gee, I should have this already calculated so that I don't take time doing this, times 2, and it's 3352 kilojoules. Because we have twice as much, it'll take twice as much energy to form it, right? Or to break it up. In this case, we're breaking it up. All right, what if we're going to form it? I just said the word form it because I had that in my mind. Let's take 2 moles of aluminum, and let's see if we would put it with 3/2 moles of oxygen gas. Could we form aluminum oxide? Well, whether we can or not, we can show how much energy it would cost us, or we would get, if we could. Now, this is exactly the same equation as the top one, right? But it's going the other direction. So if it costs us energy to break up the bonds, which is pretty normal, it always costs you energy to break bonds, and you get energy when you form bonds. So then it would be the opposite. We're getting energy out, so it's negative. Exothermic is negative energy. Endothermic, we're having to put energy into it. We have to show how much. It's positive. In this case, this last equation we just wrote down, we are breaking some bonds. We're breaking some bonds between oxygen and oxygen in the oxygen molecules. But we're forming more bonds than we're breaking, and so therefore it's going to be exothermic. It has to do with what kind of bonds we're breaking and which kind of bonds we're forming, but also how many bonds there are is going to have a big effect as well. So in this case, it's exothermic. What if I wanted to know per mole of aluminum? Well, then I could just divide everybody. And I would have divide by 2. 2 divided by 2 is 1, of course. 3/2 divided by 2. Oh my goodness, we got 3/4 now. Oxygen, gas. You know, when you first started balancing equations, we told you could never do this. But I guess we lied to you then, because we really can do this in specific cases where it serves our purposes. So now we need 1/2 of 1676, because we're only using half as much of the reactants and forming half as much of the products. We're only going to get out half as much energy. So we would get out 838 kilojoules instead of 1676. Now, this is all kind of how you manipulate these things and get different amounts of energy for different multiples. But what if you don't have just a plain multiple of 2 moles or 4 moles or 3/2 moles or whatever? What if I would tell you you had 15 grams of aluminum and it was being formed from aluminum oxide? Okay. And I say, how much energy, how much heat is required? Because we know that forming aluminum from aluminum oxide is endothermic. It requires energy. We know that from our first equation. So now, this is really not too hard. We take 15 grams of aluminum, and our balanced equation is going to tell us something about the energy, right? It also tells us about the energy that it requires for moles, not for grams. So we're going to have to put in a conversion factor. And, of course, you've all done this before. So you know that aluminum is 26.98 grams per 1 mole. Okay, the molar mass is always grams per mole. And, of course, we can flip it upside down whenever we want to. So we have aluminum here. Now, this is the cute, tricky part that we get to do. We now are in terms of moles of aluminum, but looking at that first equation, we can say, look, moles of aluminum, kilojoules, no problem. We know that we get out 1676 kilojoules for every how many moles of aluminum? Oh, look at the coefficient, 2 for every 2 moles of aluminum. And there we are, that's our calculation. So now what we need to do is take 15 times 1676 and divide that by 26.98 and divide it by 2, and we get, oh goodness, so hard to read the decimal point on this silly calculator I have. I need a better calculator. 466 kilojoules. Now, does this make sense? Does this amount make sense? Let's look at it. Okay, if we have 15 grams, that's kind of sort of about half a mole, and we know that we're going to get about 1,600 kilojoules out for 2 moles. So this is about a fourth as much as what we're talking about for the first equation at the top of the page. So we should get about a fourth of the energy required, and 16 divided by 4 is 4. So hey, looking at that, just estimating, we've got the same. We're in the right ballpark. So that's a good thing. Okay, so what the upshot of this is you can look at any thermochemical equation. In other words, by a thermochemical equation, I mean something where we've written out the chemical equation and we have the exact amount of heat either required or produced by that equation, written as a delta H out to the side. And it's just like one of the reactants or products. We can just make a conversion factor with that amount. We could have made a conversion factor with 1 mole of aluminum oxide. We could say that that's 1676 kilojoules if we needed to go from kilojoules to moles. And sometimes your problem gives you kilojoules, you have to go to moles. We could have made a conversion factor for the oxygen. We could have said 1676 kilojoules is equivalent to 3/2 mole of oxygen. And if we were going from moles of oxygen to kilojoules, that would be a perfectly good conversion factor to use. One more way we can write these equations is we can put the kilojoules in as the reactant or a product. Now, in our first equation at the top of the page, where we have aluminum oxide turning into aluminum and 3/2 mole of oxygen, is that energy being used or is it being produced? Well, this is an endothermic reaction because delta H is positive. That's always true. Endothermic, delta H positive. Exothermic, delta H negative. So in this case, it's positive. It's endothermic. Heat is being required. We have to put heat in. So heat is kind of like one of the reactants. So we could put this over here as a reactant. We could say 1676 kilojoules plus aluminum oxide is going to produce 2 moles of aluminum solid plus 3/2 mole of oxygen gas. And you see that I just wrote it in as a reactant. If it were an exothermic reaction, if it were negative, I would have put it on the product side because the energy would be being produced. And so let's just take the last equation of the 4 that we have up top. We have these 4 equations up top, right, that we made from each other. Okay, let's take the last one and let's write it this way. So if I have aluminum solid plus 3/4 O2 gas, and it's going to make 1/2 aluminum oxide solid. Now I'm going to put plus 838 kilojoules because that's the amount for this equation, because we have, remember, we reduced the coefficients, but also it's a negative. Now, don't be confused by the fact that even though it's a negative, I've put a plus in the equation. When we write it as the thermochemical equation above, the fact that heat goes in is indicated by delta H equals plus. The fact that heat goes out is indicated by delta H is negative. But down below, at the bottom of the page here, where we have these 2 equations written, heat on the left means the heat's going in. Heat on the right means the heat is going out. And of course, in a chemical equation, we can never have a minus. We only can have pluses because we have to add things together and show what's there, not the lack of them. So we would just put it on the left or on the right to show if heat's going in or out. It's just a different way of writing it. Most of the time you'll see it written like the top equations, but don't be confused by when you see it written this bottom way.